So in today's video, we're going to go ahead and continue looking at optimization for single variable calculus. We're going to do a problem that is a little bit more advanced, and I got this question off of Khan Academy, to be completely honest, because getting the numbers to work out nicely is quite difficult to prepare from your head. But anyways, so here we have a very common question that you'll see on IB or AP calculus exams. It tells you that a piece of paper is to display 150 square inches of text. If there are to be 1-inch margins on the sides and the top and a 2-inch margin on the bottom, then what are the dimensions of the smallest piece of paper that can be used? And so I kind of went ahead and drew out a sketch of what the situation may look like. So we have this piece of paper over here. We have the 1-inch margins on the sides. We have a 1-inch margin on top. I didn't include the units, obviously. Then we have a 2-inch margin down at the bottom, of course not drawn to scale. And so essentially, what we can do over here is we're going to try to create a function. We're going to try to kind of optimize that function or minimize it in order to determine the dimensions of the smallest piece of paper. And so let's go ahead and say that this length over here that I'm highlighting, right, and you can use this side length as well because these are the same, it's a rectangle. Let's say that this is going to be x. Let's just call it x, right, some random dummy variable x. So we know that this side is also going to be x, right? And they tell us that we need to display 150 square inches of text. So it means that this entire area over here that I'm highlighting, which I'm actually going to go ahead and remove the highlighting now because we're going to need to maybe write a little bit on the inside. This entire area is going to be 150 inches squared, right? And so let's go ahead and maybe also label the top over here. Let's call this y. We can go ahead and do that for the bottom as well. And we know as a result that x times y is going to be equal to 150 because we know that the area is 150. And so if we were to solve for y in terms of x, this tells us that y equals to 150 over x. And we're going to need that in a moment, that relation over there. And so we have that. Now we can go ahead and do is we can define another function. I'm just going to call this function a tilde. It's just going to be another function, right, which refers to the area of this entire, and I'm actually going to use a different color. I'm going to use green. It refers to the area of this entire square right over here. So this entire square over here, right, and let me go ahead and complete the highlighting. And so we know that based on the information we've been given, that this length over here, this length right over here, is going to have a measure of x plus 3, a length, I don't know why I said measure, of x plus 3, right? Well, because we know that we have this interior box with a length of x, and then we know that we have a 1-inch margin at the top and then a 2-inch margin down at the bottom. And so we know that this entire length is going to be x plus 3. And then we have over here that this length down here is going to be y plus 2, right? Because we have these 1-inch margins over here, and we know that the length is going to be 2. Or is going to be y. We have this y over here from the inner box. And so if we want the total area, this a tilde, it's going to be x plus 3 times y plus 2. But then what is y? We said that y is in fact 150 over x. This is going to be equal to x plus 3. We can go ahead and just substitute. We get 150 over x plus 2. And then we can just multiply this out. So we'll end up with 150 plus 2x plus 450 over x plus 6, which is going to be 156 plus 2x, no, plus 26, plus 2x, plus 450 over x. And so like I said, now it's all just your calculus 1. It's very simple in order to actually maximize this function, or to minimize this function rather. But the most difficult part is really just defining a function in the first place. So this is a tilde, right? And we can go ahead and take the derivative to continue, or to minimize this function. We'll end up with 2 minus 450 over x squared, right? And we can set this equal to 0. We're going to assume that x is not equal to 0, obviously. And then we can multiply everything by x squared to end up with 2x squared minus 450 is equal to is equal to 0. And then we get that 2x squared is equal to 450. And then this tells us right over here that x squared is equal to 225, and therefore x is equal to 15. right? And so that right over there would be our side length for this interior box. It's equal to 15. And same thing for this x down here, it's equal to 15. And so now we have, for this interior box, we have the first dimension. Let's also try to figure out what y is now. We know that y is 150 over x, so y is equal to 150 over 15, which is in fact equal to 10, right? And so y is equal to 10. And this one over here is also equal to 10. But be careful, our answer is not 10 by 15 inches. As a matter of fact, we have to keep in mind that we're asked for the dimensions of the smallest piece of paper, not the portion where we have the text. So we're talking about the entire paper, including the margins. And so let's go ahead and think about that. So this length over here, right, is going to be y plus 2. And we know that y is 10, so this is going to be equal to 12 inches, right? And then this other length over here, x plus 3, we know that x is equal to, we said that x was equal to 15, so 15 plus 3, that's 18 inches. And so therefore, our final answer is 18 inches by 12 inches. Or 18, you can also write it 18x 12 inches, right? And so that would be our final answer right over there. And you can actually go ahead and verify that x equals 15 is a minimum for this function. If you would like to, you can go ahead and just determine the sign of a prime or a tilde prime and see how it changes from a negative sign to a positive sign at this critical point over here. And so this essentially marks the end of our calculus 1, or differential calculus 1 journey, I should say. And I definitely encourage you to review these types of problems prior to your AP or IB exams, because these are very common optimization problems that you will see. And the main idea of optimization is just seeing how you can apply your concepts from geometry, from algebra, and just, general daily applications to create a certain model in calculus, and then of course optimizing that using your principles of calculus 1.